Hello. In this WAGO tutorial, we will show you how an IPv4 address is structured, what a subnet mask is, and when you need a gateway. There are many ways to send a data packet from one device to another. The most common is the Internet Protocol, or IP for short. There are generally two different versions of the Internet Protocol, the older version 4 and the newer version 6, which will replace version 4 in the future. In this video, we will focus on version 4. Namely IPv4 networks, as this is the standard for communication between controllers and other network participants. Network nodes are called hosts. To enable data to be transferred from one host to another, each host needs a unique IP address, which is unique on the network. If two nodes have the same address, this is called an IP address conflict, and data transfer, namely communication, is no longer possible. We begin by setting up a very small network. We use an Ethernet cable to connect our PC to a controller via their respective Ethernet interfaces, so that both the PC and the controller become hosts, and we need to manage the IP address allocation. An IPv4 address is made up of 4 octets. Each octet consists of 1 byte, which is 8 bits. This means that each octet can represent an integer from 0 to 255, for example, like this. Similar to a telephone number, an IPv4 address consists not only of a host address but also a network address, which corresponds to the area code. And just like a telephone number, the front part is the area code, namely the network address, and the back part is the number of the connection, namely the host address. The subnet mask is used to indicate where the host address starts. A typical subnet mask is 3 times 255.0. In this subnet mask, all the octets of the IP address that are opposite a 255 octet in the subnet mask belong to the network address, and the 0 octet identifies the host addresses. The network and host parts can be separated at any point, so a subnet mask of 255, 255, 254.0 would be possible. But how is the address space then divided? To answer this, we need to look at the machine level, specifically at how the PC or controller ultimately processes the IP address. At the machine level, calculations are done with bits, which are often represented by zeros and ones. As already mentioned, 1 octet of the IP address corresponds to 1 byte, which consists of 8 bits, that is, 8 positions that can be either 0 or 1. If we convert the number in the first octet to 8 bits, we get the following bit sequence. In exactly the same way, we calculate through all the octets, and our IP address is now fully represented as a bit sequence. We do the same with the subnet mask. 255 is represented by 8 ones and 254 by 7 ones and 1 0. We can now clearly see how the network and host areas are divided. Any bit that is a 1 in the corresponding position of the subnet mask belongs to the network portion, while any bit that is a 0 belongs to the host address portion. The computer uses a simple AND operation to calculate the network address. After the AND operation, the network address remains, and the host portion is filtered out as zeros. However, this also means that we cannot specify just any number in the last octet of the subnet mask, but only numbers where the front part consists of ones and the back part consists of zeros when bit-coded. With 8 bits, there are exactly 9 numbers. But we will stick with the very popular subnet mask of 3 times 255.0. This leaves the addresses from 0 to 255 for the host range. The first address, which is 0, is the network address and should not be used for hosts. The last address of a subnet is the broadcast address, which can be used to reach everyone on the subnet. In our case, this is 255. It is no coincidence that these are the only addresses consisting entirely of zeros or entirely of ones in bit-coded form. This leaves us with an address range from 1 to 254, where 1 is often used by a router or similar device. We can therefore assign an address between 2 and 254 to the PC and the controller. To establish a connection between the PC and the controller, they must be on the same subnet. This means that all the numbers in the IP address that represent the network portion must be the same. and the subnet mask must therefore be identical for both devices. The host addresses must be different, otherwise there will be an IP address conflict. We assign the address 192.168.110 to the PC and 192.168.100 to the controller, each with a subnet mask of 3 times 255.0. If we now enter the IP address of the controller in the web browser, the web-based management of the controller opens and we are connected. But what is the gateway column for? Quite simply, it is used to specify a gateway. In networking, you usually want to communicate not only within a subnet, but also across subnets. There are devices that can perform this gateway function. Our WAGO controller, for example, can perform this function. It has 2 Ethernet interfaces that are initially configured as switched. This means that both interfaces run on the same subnet with a common IP address. This is ideal for easily connecting additional subnet participants. However, it is also possible to separate the interfaces. In this case, the controller becomes a gateway, and we can assign each Ethernet interface its own IP address in different subnets. The PC is connected to our controller, and the IP addresses have been assigned as before. However, the controller is to be used not as a switch, but as a gateway. Because we have another controller configured with an IP address of 192.168.42.21 and a subnet mask of 3 times 255.0, which is a different subnet. In Ethernet settings, we first separate the interfaces and assign the controller an IP address for the X2 interface in the 42 subnet, between 2 and 254. We also need to enable IP forwarding through multiple interfaces in the web-based management so that data packets are passed from one interface to the next. You can find out more about this in the static routing with the PFC video. The gateway is now set up, and we should be able to use the PC to access the web-based management of the controller on the other subnet via the gateway controller. But it doesn't work because the PC doesn't know that this gateway to the other network exists. So we need to tell the PC that there is a gateway, and that's what the gateway column is for. The PC still doesn't know about the other network, but it does know about a gateway to which it sends all requests that are not on its subnet. The gateway, our controller, knows both subnets and can then forward the request accordingly. If we now type the IP address of the controller on the other network into the web browser again, we get the same error message. But why? We specified a gateway, didn't we? The problem with this setup is that only one direction of communication is currently configured correctly. We send the packet from the computer to the gateway because the destination address is in a different subnet. The gateway knows both subnets and correctly forwards the packet to the controller. The controller opens the packet but does not know what to do with the sender or where to send the response packet. So we also need to inform the controller on subnet 42 that there is a gateway to another subnet. In the Ethernet settings, we tell the controller on subnet 42 the address of the gateway controller, which is now, of course, the address for the X2 interface. If we now enter the IP address of the controller on subnet 42 in the web browser again, the web-based management interface opens without any problems, and we are connected.